Today, let us start with magnetic circuits and transformers. Okay. Suppose I have a coil, okay, like this. Let me draw symbolically. And it has some inductance. And let us ask, how much is the inductance if we know the number of turns, the size, and all the parameters of this coil. Okay, so suppose before that, if we have the current flowing here I, then what happens? We will have magnetic flux lines like this. There will be infinite number of such lines. I am just drawing a few of them, and so on. Okay. Now consider one particular turn, maybe this one. Okay. Just consider one turn, or say kth turn. And suppose the flux going through this kth turn, that means the amount of flux that crosses this turn is phi. Okay, phi k, say. Phi k is the flux through kth turn. Then definitely phi k is a function of I, the current, and it will be actually proportional to the current, and let the constant of proportionality be Lk, some constant. Then since I may change as a function of time, then phi k will also change, and according to Faraday's law, d phi k by di dt, d phi k by dt will be equal to EMF induced in this kth coil. Now there are, kth turn. There are so many turns, and all the turns are in series. Okay, all turns are in series, and there may be different amount of flux going through different coils. Okay, so the total EMF induced will be sum of ddt of phi, total phi k. Phi, say phi 1 plus phi 2, etc. So sum over k, phi k. This is what I can write. Okay. Now, if I assume that the same amount of flux goes through all the coils, okay, and if the number of turns is n is the number of turns, then we can write this EMF as ddt of sum of phi k, which is n times phi, if it is same for all the coils, and ddt of that. Okay. Now this quantity n times phi, this is called, let me represent that with the letter psi, and this is called the flux linkage. Actually, if phi k is not constant for all the coils, then psi will be actually the sum of all phi k's. If we assume that it is same for all the coils, then psi is equal to n times the flux phi. Okay, so this is more precise definition of flux linkage. Okay, so therefore what do we see? EMF induced is equal to d dt of psi, which we are approximating as d dt of n times phi, assuming the phi is constant through all the coils. Okay, so that's the expression of EMF. Now we need to know how much is phi k to get the value of EMF. Okay, so how much is phi k? To calculate phi k, we need to know the flux paths beforehand. Okay, so you may find out the paths or these lines experimentally or through computer simulation, whatever you do, but suppose we already know the paths through which this flux go. Now consider one tube of flux, maybe like this one. Okay, this and then this. Consider the interior portion of this tube, and let us ask how much is the flux going inside this tube. Let me call that delta phi. That is the flux going inside this tube. And suppose at any point the cross-sectional area of this tube is A. That is the cross-sectional area. Then we have flux lines like this here, and we can calculate the flux density in this small region. Let me call that B. That will be equal to delta phi by A. A is the cross-sectional area of this flux tube. Okay, and then if you recall your higher secondary physics, we define magnetic flux intensity vector H as B by mu. Mu is the permeability of the medium. H is also called auxiliary magnetic field. Okay, whatever you call, H is equal to then delta phi by A, right? And then according to Ampere's circuital law, we know that H integration of H dot H dl that is equal to, so if I integrate the value of H over say this closed path inside this tube, okay, integration over a closed path, that will be equal to current enclosed by that path, current enclosed. Okay, so if I assume the current in all the coils is I and the number of turns enclosed by this tube equal to n, so then this is equal to n times I. Okay, so this n, I mean this need not be, I mean this tube need not enclose all the turns. Okay, for example, if I had considered a tube here, then this does not enclose this coil and this turn and this turn, so n may be different. Okay, Achha. Then from here we can write H is equal to delta phi by A. Okay, I missed mu here, sorry. Okay, so integration of delta phi by mu A, that is equal to Ni. From this we write, and delta phi is constant because we are considering only the interior part of this tube, and throughout this tube the flux is constant, delta phi everywhere. So here delta phi, here also delta phi, the same flux goes everywhere inside this tube. Okay, so therefore I can write this delta phi outside this integration, and thus we will get delta phi equal to Ni divided by, oh I miss dl here, Okay, here I have dl divided by mu a. A is the cross-sectional area anywhere along this tube, which also is a function of the position. Here the cross-section is smaller, here the cross-section is larger. Also, mu may be a function of position if the medium is not uniform. Okay, so this is what we get finally. Now, this equation looks similar to Ohm's law. Do you see how is that so? How this is similar to Ohm's law? Okay, for that, let us first consider Ohm's law. Suppose I have a conductor, maybe like this, and the two ends are at two different potentials, say E1 and here E2. So therefore, we will have current flowing through this conductor. Suppose this is the path of the current, okay, and suppose the total current is I from left to right side. How can we get the value of I? Okay, I is the total current from left to right side. So we can get that using Ohm's law. According to Ohm's law, I will be equal to E1 minus E2 divided by the resistance of this conductor. And how much is the resistance? To calculate resistance, we may break this conductor into small slices like this. Okay, now you consider one particular slice. Suppose the length of this slice is dl, and the cross-sectional area, okay, so I mean this area is A, okay, so this area here. Then how much is the resistance of this slice? That we can write as, so here I write E1 minus E2 divided by the resistance. Now the resistance of this particular slice is rho dl by A. And now if I add the resistance of all these slices which are in series, okay, so I have to integrate it over the length of the conductor. So that's the Ohm's law. And the denominator, integration over L rho dl by A, is the resistance. Now you see that this equation and this equation looks similar. Okay, so here, so if I just compare these two equations, let me make one more copy. Okay, and let me compare these two equations side by side. Okay, so here I is current, here delta phi is flux through a flux tube, okay, through a tube, flux tube. Here the current is through a conductor. And then E1 minus E2, this is the EMF between the two ends of the conductor, potential difference. Analogously, in this equation, the term in the numerator Ni is called MMF, magnetomotive force. And then here integration of rho dl by A over the length, this is the resistance. Analogously, similarly, integration over dl by mu A is called the reluctance of that path, reluctance of that tube. Okay, so here we have the resistance of the conductor. Here this term is called reluctance of that closed path. Okay, now this resistance you may also write this as integration over L dL by A and sigma A, where sigma is called the sigma is 1 over rho. Okay, and if we call rho as the resistivity, then sigma is called the conductivity. Analogously here, this term mu is called the permeability. So you see the equation of flux and the equation of current, they look similar. So yeah, and then now let us go back to the original situation here. Originally we wanted to find out the inductance of this coil, okay, and for that we need to know the flux going through each of these turns. Okay, acha. Here we find out that the EMF is given by, okay, so this is just an approximation. Yeah, so sum of ddt of phi k, so we may, and EMF is also equal to inductance multiplied by di dt. Okay, let me write here. Then, acha. So let me just write below. So EMF is equal to L times di dt. From this, we can define L equal to EMF divided by di dt, and EMF is nothing but ddt of sum over the flux for all the turns, and here I have di dt. Okay, so therefore you can also and this term is called, as we said, is called psi. Okay, so if so, then the right hand side becomes psi by I, or flux linkage per unit current. Okay, so that is the expression for the inductance. So this is equal to L. Okay, fine. Achha. Now,
Sir, can you once
yes,
that equation which you have written for the tube B equal to delta phi by A?
This one here.
Yes, sir, this one.
Yeah, any question here?
Yeah, can you show it in the tube? What does it denote?
Yeah, so by this tube, I mean actually, let me first draw. Not this actually. Okay, I mean this tube. Okay. How much flux is going through that inside that tube is delta phi. Okay, any questions so far here?
No, sir.
Okay, so now, so we got how to calculate delta phi through one particular tube. Okay, then you can consider another tube, maybe let me draw in red, maybe this one, not this one yet, this red tube. How much is the flux here? Okay, so suppose that is delta phi 2, and in this way, if we add all this delta phi for all the possible paths, all the possible tubes, we will get the total flux. Okay, so we saw how to calculate delta phi. So delta phi, this was equal to, as we have calculated here, okay, Ni by divided by the reluctance of the tube. And now if we add delta phi plus delta phi 2 plus dot 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 for all the possible paths, we will get the total flux. Okay, and now if we multiply this with n, the number of turns, we get the flux linkage, approximately, of course. Assume, and if you want to do more precise calculation, you can do, no problem. Okay, and once we know the value of psi, then you can get the inductance. L will be equal to psi by I. Now, in this method, the main difficulty is that we assume that we know the paths for these tubes a priori beforehand. But what if we do not know these paths? Then this method cannot be applied, because you cannot do this integration, or along any arbitrary path. You have to do it along the lines of magnetic field, along the magnetic field lines only. So if you do not the magnetic field lines a priori, you cannot use this method. Okay, but now consider a different situation. If I have a magnetic core, okay, suppose like this, okay, I am trying to draw the 3D representation of a core. Okay, let me get rid of this. Okay, so can you visualize what I am trying to draw? And then suppose I owned a coil on top of this. Now this coil will also have some inductance, and let me find out how much is that. Now what happens when we have a core, and this is a magnetic core like iron or some magnetic material? Then when we pass the current, it will create magnetic field. It will create magnetic field even if the core is not there. But when we have a magnetic core which is made up of small tiny magnets, okay, there are lots of tiny magnets in this material, and they are normally randomly oriented in arbitrary direction, so there is no overall magnetic effect of the core. But when we pass this current and this coil generates some magnetic field, then all these tiny magnets, north, south, etc., they will get aligned in the direction of the magnetic field, and they will get aligned maybe like this. Okay, and there will be many more throughout the core, but all of them will get aligned north, south, like that, north, south, north, south. And all these tiny magnets, they have their own magnetic field. So now the magnetic field due to the coil alone and the magnetic field due to these tiny magnets, they will superimpose, they will get added. Okay, so let me draw, say, the magnetic field of one particular tiny magnet. Maybe that is like this. There are many more field lines. They will get added with the magnetic field of the coil alone, and as a result, what will happen is this core will act like a guide for the magnetic field lines. So it will act as the guide for the field lines, and we will have magnetic field lines passing through the core like this. Okay, there will be also some magnetic field lines which go outside the core. Definitely there will be some, but inside the core the strength of the magnetic field will be much more, because inside the core these tiny magnets get aligned and their fields are also superimposed with the original field, and therefore inside the coil field will be much more stronger than outside the core. Okay, so field inside the core will be much more stronger than outside. Also, one more fact, as I stated, the core guides the path for the field, path of the field. So therefore, we may assume that this core is along the magnetic field lines, or magnetic field lines are basically along this core only. Okay, approximately that is true. And now once we know the approximate path for this field lines, we can calculate the inductance of this coil. Okay, so now what we will do is this. Suppose phi is the flux that goes along the core. So phi is the flux along the core. Okay, and suppose the cross-sectional area of this core is A, of this core, and suppose this cross section is constant throughout, which may not be the case actually. Okay, but let us assume that this is approximately constant, this cross section, and suppose the mean length, average length of this core along the magnetic field is L. Okay, so suppose L, let me write little l, is the average path length of the flux lines, and suppose mu is the permeability of the core, which we may write as mu 0 times mu r, where mu 0 is absolute permeability of free space and mu r is the relative permeability of magnetic material, okay, of iron or whatever we have. Then let us calculate how much is phi. Okay, then yes, any question? Then B, flux density anywhere inside the core. Okay, so here how much is the flux density, or here that is B, constant everywhere, because cross sectional area we are assuming constant. So B is therefore phi by A, and then H magnetic field intensity or auxiliary magnetic field, that is equal to B by mu. Mu is mu naught mu r, so that is phi by mu a. And then we know integration of H dl, that is equal to the current enclosed by the path, so which will be I times n, where n is the number of turns approximately. Okay, and then since h is also constant throughout the path, we can write this as h into L. L is the average path length. Okay, so from this, what do we get? We so this is equal to phi by mu a times L. So from here we get phi equal to n by L by mu a. Okay, and then from this we can write how much is psi. Psi is flux linkage, which is approximately equal to n times phi, assuming same amount of flux goes through all the turns. So then this becomes n square by L by mu a. L by mu a. I missed something.
Yes, and I.
Yes.
The current.
Yeah, here I have missed. Okay, so here also I have I. Then, if so, then inductance of the coil will be flux linkage per unit current. So that is n squared by L by mu a. That is the expression of the flux, inductance of this coil. Okay. So any questions so far? Achha. Now, what happens if I have a core which is not of uniform cross section, maybe? Okay, so suppose I have a core like this. I'm only drawing the 2D representation, 2D view, front view of the core, and here I have the coils. Then how much is the inductance of this? Yes, any question? Okay, so in this case, what we can do, since the cross section is not constant, we may break the core into small sections, maybe like this. Okay, so this is one section, then this is another section, then this is another section, then this is the last one, and then for each of these sections we can calculate the reluctance. Okay, so suppose this length is L1, this cross section is A1. Okay, then for this part, how much is the reluctance? So for this part, reluctance will be equal to 1 by mu times L by A, L1 by A1. Then for this part, the reluctance will be, so let me just write curly L for reluctance. For this part, that will be how much? 1 by mu. If this length is L2 and this cross section is A2, so then that will be 1 by mu L2 by A2. Similarly, you can calculate the reluctance for this third part and fourth part, and they are all in series. So total reluctance will be, okay, so let me call it reluctance 1, reluctance 2, etc. So then the total reluctance will be just sum of L1 by mu A1 plus L2 by mu A2 plus ... You can add them up. So you can get the total reluctance, and then how much will be the flux? If that is phi, phi will be MMF by total reluctance. So MMF of this path is N times I, N is the number of turns, and total reluctance we already calculated by adding the reluctance for individual paths. Okay, so we can get the total phi, and then from this we can get the flux linkage, which is N times phi. Okay, so that will be N square I by reluctance, total reluctance, and therefore self-inductance L will be psi by I, that is N square by R. So you can calculate or estimate the inductance in this way. Okay, so we call it a magnetic circuit because these equations, MMF by reluctance is very similar to EMF by resistance for electrical circuit, so we call it a magnetic circuit, and you can calculate magnetic flux and other quantities in this way. Okay, so is it fine so far? Achha, then next, suppose
Sir,
yes.
So resistance is an opposition to flow of charges. What is reluctance if we try to understand it?
I don't
what
want
does it
see, this is a problem. When we put anything in language, in English or in any language, then there is a risk of conveying because the English language can be interpreted in different ways. All of us can interpret in different ways. So the science is done by which language? Which language is best suited for science? That is nothing but mathematics. So it is best to say that reluctance is the ratio of the MMF divided by flux. So that's the best way of saying that, and I don't want to use any other statement because you can think in that way, but I don't know whether that will convey any misconception or anything. Okay, so better to stick to mathematics. Okay.
Sir, what does the MMF stands for? Means the current, total current.
MMF stands for, again, I will just use the equation. So we, as we saw that here, within a flux tube, the amount of flux is given by the ratio of two quantities. Okay, the numerator is called MMF because this equation looks similar to Ohm's law's equation, Ohm's law, and in Ohm's law the numerator is called EMF. So in that sense, this is called MMF. Okay.
Okay, sir. Got it.
Okay, fine. So now let us consider a magnetic core, and now suppose we have two coils, one here, another here. Now, since we have two coils, let me call this current I1, and let the second coil be open circuited, so there is no current. But we have some inductance of the first coil. Let me call that L1. The second coil will also have inductance, and if I close this path, then, and if there is a source, Okay, and then there will be some current, and then to get the value of current in the second coil, you need this inductance L2. Okay, Achha. But how much will be the value of L1 if R is the reluctance of this core along this path? Okay, so R is the reluctance of this path. Then how much is L1? As we just saw, this is here n squared by R. So now if N1 is the number of turns of the first coil, this will become N1 squared by reluctance. So similarly, how much will be L2 if I estimate the inductance, self-inductance of the second coil? That should be N2 squared by R, if N2 is the number of turn of the second coil. But now we are going to consider mutual inductance between these two coils. Okay, so suppose the second coil is open, there is no current, but the first coil has some current, I1. And if I1 is a function of time, so that can change as a function of time. So therefore, this flux that flows through the coil, that will also be a function of time. And this flux is also going through the second coil. So there will be some EMF induced in this between the two terminals of the second coil. And how much will be that? That EMF is by definition M, call it M12 or M21, whatever, M21 dI1 dt. That will be the EMF between the two ends of this second coil. However, we can also calculate this EMF considering this flux. Okay, so how much is the EMF induced in one particular turn of the second coil? Let's call that E2. That will be d phi by dt. But this is the EMF in one particular turn. But all these turns are in series, they are connected in series. Therefore, the total EMF will be multiplied by N2, assuming same amount of flux phi is going through all the coils. That may not be the case. Maybe there is some flux which goes only through this coil but doesn't go through other coils. But assuming that the same amount of flux goes through all the turns, the EMF induced in the second coil will be d phi d2 multiplied by N2. Okay, and how much is phi? Phi is nothing but MMF N1 I1 divided by reluctance, that is phi, now ddt of that, and N2. Okay, so we have here N1 N2 by reluctance di1 by dt. So from this, what can we say? How much is M21? Okay, M21 should be N1 N2 by the reluctance. Okay, in the same way, now if I assume that the first coil is open and there is some current in the second coil, I2, and I2 may be a function of time, therefore there will be some mutually induced EMF in the first coil. How much will be that? That will be M12 di2 by dt, and you can also find out the value of M12. How much will that be? Can you guess? M12 will be, just replace N1 by N2 and replace N2 by N1 in this equation. So if you do that, you will get same thing. So once again, we see that these two are equal. Although this is an approximate result, okay, still we see M12 and M21 are equal, and they are actually equal, exactly equal, that we saw in our last class using the concept of energy conservation. Okay, acha. Now, so we got L1 is this, L2 is this, and the mutual inductance is this much. Next, one more question remains. Okay, when I write the voltage like this between the two terminals, say, let me call it A, B, and C, D, this is incomplete because I am saying the voltage between C and D is M21 di1 dt, but I still don't know which side is positive, which side is negative. Is C positive or is D positive? How do we know that? Which side positive? Or which side is at higher potential? Okay, so let us ask this question and see what can we say. Okay, so now we have only current in the first coil, and here current is 0. Now, and I can just write it M di1 dt because M12 and M21, they are equal. And which side is positive is the question we are finding. Okay, so for this we will use Lenge's law. Now, assume I1 to be positive and is in this direction. If so, can you find out in which direction the flux will be in the core? Will it be in the clockwise direction or will it be in the anti-clockwise direction? If the current is in this way, if you use right hand rule, you will get flux in clockwise direction. This is phi. Now this suppose di1 dt is positive. di1 dt is positive. Suppose that means this flux is increasing in the clockwise direction. Now which side between C and D will be positive? Okay, so there are two possibilities. One possibility is that C is positive, D negative. The other possibility is D positive, C negative. In other words, there are two possibilities. One is that the induced EMF will try to drive a current in this direction, like this, or it will try to drive the current in the opposite direction. Which direction is correct? In
Previous direction.
So see, d phi 1 dt is positive. That means flux is increasing in the clockwise direction. Flux increasing clockwise. So the second coil should try to drive a current which will generate flux in anti-clockwise direction according to Lenge's law. So that means it should try to drive the current in this direction. Okay, so these red arrows indicate the direction of EMF in second coil. Right? So the EMF must try to drive the current in this direction. Actually, the current may not be there. Whether the current will be there or not, that depends on whether we have a closed path or not. We may not have a closed path, and therefore the current may not be there. But the EMF will still be there, even if the current is not there. And in fact, the current may be in other direction depending on what we have outside. You know, we may have say a current source here, so which will drive the current in the opposite direction. So depending on what we have outside, the current may be in different direction or it may not be there at all. But the induced EMF will definitely try to drive the current in this direction. That is for sure, that is from Lenge's law. So therefore, which side should I call positive and which side as negative between C and D? The answer is this, plus here, minus here, because this coil will try to drive the current in this direction. Okay, so C is positive, D is negative when di1 dt is greater than 0. Any questions so far? No? Okay. So now recall what we have learned in our last class about dot convention. If we have two coils, and the mutual inductance between them is M, the current in the first coil is I1, the voltage in the second coil is, due to the first current, will be dm times di1 dt. Now, in which direction this mutual voltage m di1 dt works? For that, to find that, we need dot convention, dot symbol. Suppose the dots are here. And what does the dot convention say? It says, if current I1 is entering one dot, then for the voltage m di1 dt, the other dot should be positive. I mean, m di1 dt is the voltage of the other dot with respect to the non-dotted end. That is dot convention, if you recall. So if so, now coming back to this picture, if I put a dot beside terminal A, which side should have the other dot? Side C or side D? Which terminal should have the other dot in this diagram? Yes? The answer is side C. Okay? Then, but if I just take this core and the coil and I make a small change. Suppose suppose now this is the direction of the second coil. This is the sense in which the second coil is owned. Now, if side A is marked with one dot, then where should be the other dot? On side C or side D? The answer is it should be here. Okay. at side D. Fine, okay. So any questions so far? Okay. So did you get the idea?
Yes.
Okay, fine. So
Sir, I have a doubt, sir.
yes,
Sir, in the previous diagram,
this one.
uh, yes, sir. Sir, here it seems like the current is going from D to C, right?
Current is going from D to no. Firstly, current, I don't know. Current may not be there at
Uh,
all. So the current, I mean, the EMF will try to drive the current from D to C inside the coil.
yes. Then, sir, D should be the higher potential. Right?
No, no, no. Why? Why? See,
So,
one thing am telling is that current does not always flow from higher to lower potential. It's not the case. When is it the case? When does current flow or where does current flow from higher to lower potential? Only in a resistance and nowhere else. Okay, so what happens, say consider a battery. I guess I told this before, but let me repeat again. Suppose this is a battery, DC battery, 1.5 volt, okay, plus mine. I hope this is a good looking battery, okay. In which direction current flows? Now there is no current unless and until I connect something, but now if I connect a resistance outside, in which direction will the current flow? Minus to plus inside the battery.
yes.
So yeah. Okay, so if you compare this battery with this coil, so battery is a source of EMF, this coil is also a source of EMF, okay. So as a source of EMF, this convention is absolutely fine. So this battery tries to drive current from minus to plus inside the source. Here also inside the coil, inside the source, the coil tries to drive the current from minus to plus. Tries to drive. Actually, the current may not be there or maybe in other direction depending on what is there outside. Okay.
Okay, sir, got it. Thank you, sir.
Yeah. So next. So when we have these two coils, then we can do one thing. We can, okay, suppose this is a core and we have two coils, and here I can connect a voltage source, and here across the other coil I connect some impedance. Then what will happen? Suppose the voltage here is V1. Some voltage will be induced between the two ends of the second coil, okay, and that will drive some current here, okay. So this is V2, okay, V2 is M dI1 dt, I1 is the current here, okay, and So there is no connection between the first coil and second coil, but still if you connect a voltage in the first coil, you get current in the second coil. So this is called a transformer. Okay? And this way you can transmit power from one side to the other side without any physical connection, any conducting connection. Okay, so and here I2 will be V2 by Z up. I mean, it will depend on V2 and Z. Okay, yeah. Also, the inductance of the coil will come in picture. Okay, now in this situation, if N1 is the number of turns of the first coil and N2 is the number of turns of the second coil, okay, then, and here the applied voltage is V1, then how much is self-inductance? It is of the first coil, it is N1 squared by reluctance of the core. Okay, so how much will be this current, phasor value of current, I1? And now assume that for simplicity there is nothing connected in the secondary. Then I1 will be V1 divided by J omega L1, assuming the resistance of the coil to be negligible. You can use a very good conductor, so resistance is negligible. Okay, so anyways, this is still approximation. In fact, L1 equal to N1 square bar by reluctance, these things are all approximate results. Okay, and then how much is the voltage induced across the second coil? So we know V2, if I write it as a function of time, V2t is equal to M di1 dt. M is the mutual inductance between the two coils. And how much is M? M is N1 N2 by the reluctance of the core. Okay. Now, if I write this using phasor notation, what do you think this will look like? Okay, because this equation is analogous to the equation for a single coil, that V is equal to L di dt. This is for a single coil. Okay, and for a single coil, the phasor equation becomes voltage phasor is equal to J omega L I bar. So analogously, if you just consider this, what will be the phasor equation for relating V2 and I1? That will be V2 bar equal to J omega M I1. Okay, so therefore here we can write V2 is equal to J omega M I1, and I1 is given here. Okay, so this if you put the value, what will you get? J omega cancels, M by L1, right, into V1 bar. And M is given here, L1 is given here. So if you put the value of M and L1, what do we get? N 2 by N1
N2 of
V.
N1.
Yeah, right. But anyway, these are all approximate equations as we have seen. Okay, but the quite good approximation, very good approximation. Okay, so we see here that from we can write that V1 by V2 is approximately equal to N1 by N2. This is the relation between the two voltages for a transformer. Okay, but now we have now in a transformer we call the two coils as one as primary coil and another as secondary coil. We have considered that secondary is open circuited, so no current is flowing. Okay, and now how much will be the value of I1 under this situation? As we have just seen, it is given by V by j omega L1. Okay, so when secondary is open, we have I1 is equal to V1 by j omega L1, and so this is equal to V1 by j omega. How much is L1? L1 is N1 square by reluctance. And how much is reluctance? So that, let me write below, V1 by j omega N1 square, and reluctance is L divided by mu A. L is the length of core, A is the cross-sectional area of core, mu is the permeability of core. Now, for a good transformer, it is required that mu is very high. So we will assume mu tending to infinity. Anyway, it's not infinity, but it is very high. But if mu is tending to infinity, then how much is I1? I1 is approximately equal to 0 for a good transformer. Okay, this is when secondary is open. Anyway, I1 cannot be equal to 0 exactly, because if I1 is exactly 0, so then there is no current at all, so there will not be any flux at all, and if there is no flux, there won't be any voltage in the second coil at all. Okay, so it cannot be exactly 0. That is, that is not possible, but it is very small for a good transformer, because mu should be very large for a good transformer. This is one assumption we will use. Okay, now what happens when we connect load to the secondary side? Okay, so now let me copy this. Now we have some load here, Z. Okay, so then there will be also some current I2. In which direction, I don't know, but anyway, some current will be there. Achha. And here we have the current I1. What will happen now? Note that V1 is same as before. Okay, so V1 I am not changing. Only thing I have done, I have connected a load in the secondary side. So V1 is still same. Achha. Now one more thing, one more expression we will learn about the one relation between voltage and flux for transformer. Okay, so let me state that before this. So consider the flux here to be phi. Okay, and number of turns of the primary coil is N1. So then how much is V1? What is the relation between V1 and phi? V1 is equal to ddt of phi multiplied by n for all the n1, for n1 number of turns. Okay. Now, if V1 is sinusoidal, if V1 is varying sinusoidally, then this flux should also vary sinusoidally. Okay. Otherwise, this equation will not be satisfied. Okay. So if V1 is sinusoidal, then we need phi also sinusoidal. Now, suppose phi is varying like some phi naught cosine omega t. Okay, if V1 is sinusoidal with frequency omega, then the phi should also have the same frequency. Okay, Achha. Then how much will be V1? If you do this differentiation, we will get phi naught omega cosine, derivative of cosine is minus sine. Okay, so how much is the, and then how much is the RMS value of V1? Okay, so this we can write as phi naught 2 pi f. I missed something here, N1. Sine omega t. Okay, so RMS value of V1 t will be equal to 2 pi f n1 phi naught, this number divided by root 2, which is equal to root 2 pi phi f n1. So this is one important relation between the voltage and the flux. Okay. Now let us ask the question, what happens if we connect a load to the secondary side? Notice that this voltage is unchanged. If this voltage is unchanged, then this flux phi must also remain as before. Okay, so therefore phi as a function of time should remain same as before. Okay. However, previously only current I1 was flowing and I2 was 0. Now I1 and I2 both are flowing, both of them are non-zero. Okay. But still the flux must remain the same. How is that possible? That is only possible if, suppose I1 was equal to I1 naught when secondary was open. That means I2 was equal to 0, suppose, and suppose I1 is equal to I1 naught plus something, say I 1 when secondary is closed, that is I2 is not equal to 0. So the new primary current is previous primary current plus something extra. That's what we are saying. Then now the flux is created by three currents, I1 naught, I11 and I2. All these three components of currents will create flux. But still the flux should remain same as before. That means same as the flux that was created by I1 naught alone. So when is that possible? So we need the flux of I11 and the flux of I2 to cancel each other. Okay, so then only the flux will remain same, and we must have the flux remain same as before because the voltage in the primary is same as before. Okay, so therefore we need these two components, the flux due to I11 and the flux due to I2 should cancel each other. Okay, now how much is the flux created by I11? Okay, so the flux created by I11 will be I11 multiplied by N1 divided by reluctance. That's the general rule, MMF by reluctance is the flux. So this and I2 times N2 by R should cancel each other. Okay, so suppose here I2 is flowing in this direction. Okay, so I2 is flowing in this direction. In which direction I11 should flow such that their flux cancel each other? In this way or in this way? Which one?
Previous,
this one. So this will be the direction of I11. Okay, acha. So one more thing you notice, in this transformer, how are the dots? So if you recall, we just did it before. The dots are in terminal A, at terminal A and terminal C. Okay, so for this transformer, the dots are here and here. Okay, so we see that if current I2 is leaving the dot, then current I11 should enter the dot. Okay, so these two currents should, if one is leaving the dot, the other one should be in the opposite, should enter the dot. Okay, so if I2 is leaving the dot, then I11 should enter a dot. That is one condition. And one more condition we saw that these two should be equal, and these two fluxes should be equal and opposite. So we also need that I11 So so this are same. So this equal to I2 by this, and this R you can get rid of, they are common. So we need these two to be equal. However, I1 is equal to this, and how much is I1 naught? What is I1 naught? I1 naught is the current that was flowing when secondary was open. And for a good transformer, how much should be that current? When the secondary is open, that should be 0. So therefore, we can also write, so this implies this is actually I1 minus I1 naught multiplied by N1. This is equal to I2 N2. But since for a good transformer, this is equal to 0, approximately equal to 0 for a good transformer, therefore, what can we write? We write I1 N1 is equal to I2 N2. That's what should happen for a good transformer. This is called the MMF balanced condition. MMF balance condition. Okay, the MMF, just a second, MMF created by the first coil, which is I1 N1, should be equal to the MMF created by the second coil I2 N2, and they should be in opposite direction. Okay, as I stated that if one current is entering the dot, the other current should be leaving the dot at that moment. Okay, so they should be equal and opposite. Yes, your question.
Yes, sir. In the last equation, we do not know I10 as how much it is with respect to I1. So should we cancel that?
It is not G, but that's what we said, that for a good transformer, I10 should be equal to 0. Why? Why? Because how much is I10? When secondary is open, how much is I1? This is voltage divided by j omega L1. Okay, and L1 should be very high. Why? Because L1 is proportional to mu, permeability of the transformer, which should be very high. Okay, so therefore L1 should be very high, current should be very low.
That is what I am saying, no?
Yes. So
since L is proportional to mu, it means I1 will also not be that large, no?
I
mean to say I10 plus I11, the final
no. See, the thing is that I1 is not equal to V1 by j omega L1 when secondary is when secondary current is non-zero. When secondary current is non-zero. This is true. I mean, I1 will be V1 by j omega L1 only when secondary current is 0. In general, what is true is that V1 is equal to I1 L1 di1 dt plus m di2 dt. That means if I write it in phasor form, that it will become V1 bar equal to L1 j omega L1 into I1 bar plus j omega m I2 bar. So when I write a differential equation, I mean in phasor form, always this di ddt terms get replaced by j omega. That's the simple trick. So you just replace ddt by j omega and you get the phasor equation. So this is the general equation for V1, which is j omega, which is like this. Now if I2 is 0, then this equation will be true, I1 equal to V by j omega L1, but otherwise that is not true. Okay?
Yeah, yes, sir.
Yeah, fine. Okay, any other questions so far? No. Okay, so we saw that approximately for a transformer, V1 by N1 is equal to V2 by N2, and I1 N1 is approximately equal to I2 N2. Now let me define one thing which is called an ideal transformer. An ideal transformer, ideal two-winding transformer, is a black box, is some equipment which has two ports or sides or I mean whatever you call primary and secondary, and such that if you apply an AC voltage, and some AC voltage V1 here, then there will be some voltage induced V2 in the second coil, and V2 will be equal to V1 by N1 times N2. This statement is not complete. I also have to state the polarity of the voltages, and for that I also need a pair of dot symbols. Suppose the dots are like this, okay, then I can say if V1 is like this, V2 will be like this, and they will be proportional to each other. And also, if there is some current I2 flowing here, we will also have a current flowing I1 here, such that I1 will be equal to I2 N2 by N1, and if I2 is going out from the dot, then I1 will be going into the dot. If these two equations are satisfied, then we call this equipment as an ideal transformer. Any equipment that satisfies these two equations perfectly is called an ideal transformer. But the transformer that we saw here does not satisfy this equation exactly, so we call that a non-ideal transformer, non-perfect transformer, practical transformer. Okay? Acha. Then
can we say that the flux linkage is complete in an ideal transformer?
Flux linkage complete in the sense? Complete means?
In terms that from primary to secondary, there is no loss of the energy contained by the magnetic field.
Yeah, so since you are talking about, yeah, let me also, yeah. So then for an ideal transformer, so if these two equations are true, then what happens? Since you talked about energy, so energy input from primary side is how much? That will be V1 I1 cosine of the angle between V1 and I1, and energy going out from the secondary side, energy output from secondary side, that will be V2 I2 cosine of angle between V2 and I2. Now, from these two equations, you can readily see that the RMS value of V2 multiplied by RMS value of I2, okay, so V2 I2, that will be equal to V1 I1. Anyway, that is true. But what about the cosine terms?
Those are
They
equal.
are also equal, because so V2 and V1, they are in same phase, okay, because n2 by n1, this is just a constant number, real number. So similarly I1 and I2, they are also in same phase. So therefore angle between V1 and I1 is also same as angle between V2 and I2. So therefore these two are exactly equal. So energy is therefore conserved in the sense that this transformer, this black box itself does not consume any energy. Okay, so whatever energy comes from the left side is gone out from the right side. Okay, and there is no overall energy consumption by this transformer at all. So ideal transformer do not consume energy, do not consume or generate anything, do not consume energy. Not only that, so here, so this is basically average energy we are talking about, okay, because this Vi cos theta is the expression of average energy for sinusoidal quantities. Not only average energy, okay, so if I talk about instantaneous energy also, okay, so in terms of instantaneous voltage and current, if this is V1 function of time, this current is I1 function of time, here is a dot, here is a dot, I2 function of time, V2 plus minus function of time, here V1 is like this plus minus. Then for an ideal transformer, we also have V1 by V2 for at any time, at any moment is equal to, assuming sinusoidal quantities also, but do I need to assume sinusoidal quantities? No, not required. Anyway, this is true. V1 by V2 is equal to N1 by N2, and I1 by I2 as a function of time, this should be equal to N2 by N1. This is the definition of ideal transformer. Let me write TFO in short for transformer, and therefore you see V1 I1 is equal to V2 I2 at all time. Okay, so that means there is not also not just any overall consumption of energy, but at each and every moment there is also no storage of energy by the transformer. Okay, because this is true for all time. So that means this is also not possible by an ideal transformer to store some energy for some time and then release. Okay, ideal transformers do not even do that. But anyway, that is practically not possible. Why not possible? Because if you consider this practical transformer, then it has flux. And if it has flux, and the flux is also varying, say sinusoidally, sometimes zero, sometimes increasing. But when there is flux, there is also some magnetic energy, electromagnetic energy stored in the magnetic field. Okay? But that energy is again released after a while periodically. But how much is that energy? Okay, so how much is that energy? Let's see that in a bit more detail. Okay, so
Sir, won't there be heat also then?
heat I'll come later, but before that, okay, so suppose I have okay, suppose I have current I1 here and say secondary is open for simplicity. Now, how much is the energy stored by this coupled coils? Okay, so energy in general is half L1 I1 square plus half L2 I2 square plus M I1 I2. Okay, so if I1 or I2 varying sinusoidally, then this energy is also varying with time. But for simplicity, let us assume that I2 equal to 0. Then these two terms are not there. Okay, then this is the expression of energy at any time. And how much is I1 if we have a sinusoidal voltage here, which is V1? Then I1 is of the order of V1 by L1. Basically in phasor form, I1 bar is V1 bar by j omega L1. So you can see the magnitude of I1 depends on V1 by L1. Okay, so therefore the magnitude of energy stored, which is varying with time, that depends on half L1 in place of I1 square. Let me write V1 squared by L1 square. Okay, so now this L1 and this square can be cancelled. So this is of the order of V1 squared by L1. V1 is some finite voltage, but L1 for a good transformer, for an ideal or good, very good transformer, how much should be L1? L1 should be very large. L1 tends to infinity because this is L1 is proportional to N1 squared by what was the expression? Core length by permeability here and area of the core. Now permeability should be very large. Mu tends to infinity, ideally for a good transformer. So therefore this energy also tends to 0. Energy stored is also very close to 0. Okay, so this is one assumption for a good ideal transformer, permeability to be very high. Okay, fine. What's next? Any questions so far? Okay, so we saw.
But there will not be an eddy current in the transformer.
Oh yeah, you talked about eddy current, etc. So those things we will discuss probably next week. Not this week. It won't be possible. So yeah, those things are not there ideally.
Okay, sir.
Yeah. Next. Okay, so now suppose I have an ideal transformer. Turns ratio is say N1 is to N2. Now here I connect a source and here I connect some impedance Z. Now the question is, how much is the impedance seen by the source between the terminals A and B for an ideal transformer? How much is the impedance seen by the source? Okay, if I call this V1 bar, this current is I1 bar, this is I2, this is Z. Then how much is this voltage? V2 bar, that is N2 by N1 V1, and how much is the impedance seen by the source? Impedance seen by source will be equal to V1 bar by I1 bar. Okay, now how much is I1? I1 will be I2 N2 by N1. Now how much is I2? I2 is, anyone? V2 by Z. Here we have N2 by N1. Okay, so then V1 and in place of V2 below, I can write V1 N2 by N1, and this Z is here, one more N2 by N1. So finally, what does this become? It becomes Z N1 by N2 whole square. This is the impedance seen by the source, primary side. Okay? Now, a transformer is an equipment which, so it is transforming voltage from right side to left side in this way. Okay, so voltage from right side to left side if the right side voltage is V2, then the left side voltage is V1 N1 by V1 N2 by N1. Correct? Current. If the right side current is I2, then the left side current is I2 N2 by N1. And if the impedance of the right side is Z, okay, these are phasors, then the impedance seen from the left side is how much? Z, as we just saw now, multiplied by N1 by N2 whole square. Okay, so let me just use a simpler notation. Let me call A equal to N1 by N2, then this becomes V1 by A, this is I2A, and this is Z A square. So you see a transformer multiplies, divides the voltage by A, multiplies current by A, and impedance by A square. Now this is for
current also will be doing.
pardon?
Sir, current also, sir, should be N1 by N2 in the denominator.
Current, I made a mistake? Yes, I think I have made a mistake. I yeah, so here, yes, A
Divide.
should be below. Then here should, I think,
Sir, it should be in terms of V2, right? The left voltage.
yes, I think, yeah, so this is right. V2, yes.
N1 by
Thank you. Yeah. Okay. So voltage is multiplied by A, current is divided by A, impedance is multiplied by A square. Now, suppose I have an ideal transformer and there is some circuit here, maybe any complicated circuit that you like, you think of. This side also say some circuit is there. Whatever complicated circuit you like, you can think of. And this is an N1 is to N2 ideal transformer. Suppose all this voltage, current, resistance, impedance in general, everything is given. The question is solve the circuit. How to solve the circuit? Okay, to solve this circuit, we can do this thing. Consider the right side of now between these two nodes we can calculate Thevenin equivalent VTH, ZTH. Now consider this part. What will be the Thevenin equivalent between A and B? If VTH and ZTH is known, you can calculate then what will be the Thevenin equivalent between A and B of the right side. So here we will have the impedance ZTH multiplied by N1 by N2 whole square, and the Thevenin voltage will become VTH multiplied by N1 by N2. Okay, and then you can solve the left side of the circuit. Now suppose I do this I suppose this voltage, this current is say some I2, this is some V2, this is some Z2. Now I have copied the same circuit, but I replace this voltage by V2 N2 by N1 whole square. No, only, not square. This I replace by Z2 N1 by N2 whole square, and this current source I replace by I2 N2 N1 by, sorry, I2 divided by N1 by N2. Now in the original right side circuit, the Thevenin voltage was VTH and ZTH was the Thevenin impedance. In this modified circuit, how much will be VTH and ZTH? Can you guess? How much will be ZTH in this modified circuit? In terms
Z
of
N1 by N2.
ZTH multiplied by N1 by N2 whole square. That will be ZTH new, called it ZTH prime. And how much will be VTH prime? Between these two terminals C and D in terms of the previous VTH. You can check and you can show that this will be previous VTH multiplied by N1 by N2. Okay, so from this I can state that if I take this modified circuit and I take the original left side circuit, and I connect this right side circuit to the left side, then this is Thevenin equivalent of the original one. Okay, and now I can solve this circuit. So I will get how much is the current here, call it I1, how much is that, how much is the current here, call it I say 3, okay, how much is the voltage between A and B, VAB. These values I can calculate from this circuit. And then this VAB will be the same as the VAB that was there in the original circuit. The current here, I1, will be same as that in this circuit. And so on. Okay? So therefore, if we have an ideal transformer, then then you can take one side, say the right side circuit, and multiply all right side impedances by basically this is A square, N1 by N2 is A. So multiply all impedances by A square, turns ratio square, all voltages by turns ratio, and divide all currents by turns ratio and connect it to the original, to the left side circuit, and then you can solve it. In the same way, you can do it in the opposite way. Okay, so what else you can do? You can take the left side circuit and now multiply all left side impedances by 1 over A square. All left side voltages by 1 over A, and divide all left side currents by A and connect it to the right side circuit, and you can solve it, and you will get the solution for that circuit. Okay, so this is how we can solve circuits with ideal transformer. So basically, if we have ideal transformer, we can just get rid of the transformer itself by appropriately multiplying the voltage, current, and impedances of one side. Okay, so that's almost the time today. So I will stop here.